generating debug and deboost. So let's say this is my then okay, this is your VDD and this is your Vout. So this is your gate driver. So debug is nothing, it's a clock with a duty cycle debug. It's just nothing but PWM. This will also have gate driver and this one will be the same. Okay. So how do we generate these two? So let's say in the case of buck, now you have output. So let's say I have this feedback register R1, R2, then you have your error amp with compensation. Okay. So this will give you control voltage. If you compare this with a sawtooth, which is let us say 0 to Vm, what will you get? A PWM. This is what your buck was, huh? Now we need another. So let us say this is debug. So this is very straightforward. How will you get the boost? I mean, from the same controller we want two duty cycles here, debug and deboost. Huh? Yeah. So we need one more sawtooth with a shifted VM. So let's say I get another. Let me just. So 0 to VM, one more comparator. Can you tell me what will be the level of this? So this is 0 to VM. What will be this one? Okay. So what will be your duty cycle, buck duty cycle when V control is VM? Okay. So let's forget about 90% Dmax and everything. So where do you want to go from there after 100%? Boost mode, huh? So which means your boost sawtooth has to start from VM. So at VM your boost will be 0 duty cycle, and when it further increases, goes beyond VM, it will start increasing the boost duty cycle, and when it goes to 2 VM, it will become 100% boost. So it will look like this. Okay. So this is your Okay. So when your V control goes to VM, that high side switch in case of buck will automatically will be fully on. We already know what was the logic. When you operate in boost, you want this switch to be turned on, this guy, okay, and this turn off. So 100% duty cycle means this will be on, this will be off, and then these two switches will start operating. Okay. So if you don't have any limits on the duty cycle, it will very smoothly go from buck mode to boost mode. There is no buck boost mode as such here. Okay. There is no condition where all the 4 switches will be operating, because your maximum limit is here 100% and your minimum duty cycle in case of boost is 0%. But now if your duty cycle is limited here, so let us say this is 0.9 Vm and this is 1.1 Vm. So this is your buck boost mode, which is nothing but dead zone for buck and okay. So this is your buck mode, this is your boost mode. So you have 3 modes now. So this is saturated to, so D max is, or D buck max is 0.9 and D boost min is 0.1. So between 0.9 of your buck to 0.1 of boost, you operate in buck boost. So how will it operate in buck boost? How will you build that control? So I have only 2 options, 0.9 and 0.1. I mean 0.9 boost, 0.1 buck. I cannot get anything in between that. So what are the possibilities if you have only 2 duty cycles? How can you still regulate the output with only 2 duty cycles? We talked about it. Yeah, use pulse skip mode. You dither between 2 duty cycles. So let us say 1 buck, 1 boost. So let us say I give a 0.9 buck and 0.1 boost. This is equivalent to what? 100% duty cycle. Okay. Now if I give a, let us say 4 bucks and 1 boost. So that will be less than 100%, between 0.9 and, okay. So that is how you do. Basically you dither between 2 duty cycles and choose the number of cycles of buck and boost. So what you do actually, so in buck boost mode, can regulate by dithering between 0.9 buck and boost debug boost. Okay, which means, so let's say I have this debug is 0.9, deboost is 0.1. So from 0.9 I want to slowly change my duty cycle, but I have no option. So let's say I choose n of this, 1 of this. Okay. Then n minus 1 of this and 1 of this, n minus 2 of this. Okay. And this is your VDD is increasing or decreasing? You are reducing number of buck cycles, which means VDD is reducing. For the same output, you want to increase the duty cycle when VDD is reducing. So finally, you will get 1:1. So what do I need to do after that? Now you fix your buck and make this guy n, not n, sorry, 2, 3, and eventually you will get to n minus 1 and 1, 1, and then you make it 0, and what will be this? Which means you will be operating at 0.1 boost, because now debug is completely gone. So this will make a smooth transition between buck to buck boost and buck boost to boost. So how do we decide how many cycles we need? Let us say I choose n equal to 10 arbitrarily. So who will control this n? How will you generate this code? You need digital number to this code is digital. So there are two ways. You already have V control. After V control reaches 0.9 VM, you feed it in an ADC and generate the code. You know what is the range from 0.9 VM to 1.1 VM, that is already known. So you can resolve that where the V control is and generate the code. So you will get the code. So let's say you start from 0.9 VM corresponds to 0 code, and so let's say I have a 3 bit. Okay, so all 0 means 0.9 VM, all 1 means 1.1 VM. In between, you will get all the codes. Another way, you just use a comparator, compare the output and feed it in the accumulator. Because when you saturate the duty cycle, what will happen? Your output won't be regulated. Now, if you compare that with your reference again, this V out with the or VFB with the Vref, then and accumulate that, so it will generate your code error, just like a digital LDO or any digital controller we talked about. Okay. So both ways are possible. You can use a 3-bit or 4-bit ADC. You can do a flash, or you can have a, but accumulator will be slower. If you do with the flash, then it will be faster. So that's the difference. So depending upon how much resolution you require, you can choose whether you require a 3-bit or 4-bit. If you require 4-bit, then you will get like 15 different codes, and corresponding to that you will get So which means this range will be sliced into your fine resolution 1 LSB. So each LSB will be depending upon your number of bits you are using, correct? You guys know ADC, flash ADCR? It's just comparator, huh? So take this V control, and you require multiple references here, and compare with that, it will give you the code. Okay. So for 3-bit flash, how many comparators you require? 7. For 4-bit, 15. Okay, but it's not necessary they use flash, you can use SAR or anything. SAR is even much simpler, it doesn't require that many comparators. So, and it's more digital actually, SAR. So, okay, otherwise you need to, if you want to do in analog, then only option is just, you leave it on its own and your loop will recover, but then you have to live with that transient, or you make your loop some fast, or maybe some way to compensate, like feed forward compensation or anything to correct the duty cycle. So you can do that also. One buck boost we did, we simply changed the duty cycle. So as I mentioned, if you know the load, then from 0.9 to 0.81 when you go buck boost, and if I know the load, then I know the duty cycle also, I can directly generate the duty cycle. Okay, you have the sawtooth available, all you need to change the comparator voltage. So instead of feeding the V control, you will feed that particular voltage and it will generate some different duty cycle. So you can generate any duty cycle, that's not a problem. So you will directly force and then close the loop again. So that you will force only during transient. Okay. So it's basically like subtracting some voltage from the V control. So let's say this is saturated at 0.9 Vm in buck, and when I enter buck boost mode, what do I want? I want debug to be 0.8 or so, but this V control is still 0.9. So what you do, you take the V control, and so V control, let's say 0 to 1 volt was your ramp, so 0.9 volt. So from 0.9 subtract 100 millivolt, and that voltage will be given to this buck comparator, and that will change the duty cycle. So you have to do some math here in between. No, it won't be open loop. So in the closed loop, that you have a subtractor, So this 100 millivolt you have fed, when you transition, before that 100 millivolt is 0 actually. Okay. So the moment you transition, you make that voltage 100 millivolt, so duty cycle will immediately change, that's it. And from there it will take on and just do. And one thing you need to remember, so then again your debug will keep increasing. So it will again saturate at 0.9. So then now you have to increase the boost duty cycle, but I cannot keep always at 0.9, because ultimately you have an option to go to 100%. From 0.9 to you can jump to 100%. So I don't want these 4 switches to be always operating. If you saturate your debug duty cycle at 0.9, then even boost mode you will be operating all the 4 switches. So basically you need to keep monitoring the boost duty cycle. So let's say you go to 0.2 or so, then you can change the buck duty cycle to 100% and move your deboost back to around 0.1 or so. So that you can calculate again with the boundary condition. Okay, at what deboost you actually want to force debug 100%. So in that case, your high side switch in the buck will be always on, and so you will be entering in the pure boost mode in that case. Otherwise, you will always remain in buck boost mode. You will never come out of that if you saturate your buck duty cycle at 0.9. Okay. But if you do this digitally, then it will automatically take care of that. You are just dithering between, and here your count will become 1 for this, and at that time you force your debug 100%, which will make like a 0 cycle of debug you are forcing. So, the other switch will not operate. Otherwise, you will lose efficiency. Your switching losses will be more because you are operating all the 4 switches, and then dead time and all those. So, all the losses will be there. So, you may lose 1 or 2% efficiency if you do not do that.
Means the problem is why we cannot increase duty cycle after a certain maximum value is that means we can jump to 100%, but in that point the gate driver and all won't work efficiently.
Yeah. So, 10% I am assuming it is a hypothetical number actually. I mean, nothing special about 10%. If you, let us say your circuits are very fast and you can achieve up to 98%, then you limit at 98%. So, you do not need to limit at 90, always 90%. It could be in some cases 95%, it may be 94, 92%. It all depends on like, so you have to run at across PVT and see exactly where your circuit is not responding, what is the maximum duty cycle your circuit does not respond, and you just limit your duty cycle on that.
From that maximum we can directly jump to 100%.
You can always jump, but you will get a transient at the output. But if your loop is, let us say, fast enough to correct that, then it is not an issue, but usually it is not. Your bandwidth is limited. So, you will always get some transient. So, if that transient remains within your limit, then it is fine. But if that goes beyond, let us say I have a 5% limit for overshoot, undershoot, then if it goes beyond 5%, then you have no option, and you have to think about like this. I mean, this transition may happen during load also. So, 5% let us say margin you have kept for load, and this transition has also happened. So, it is quite possible your overshoot may go to 10% or so. But if you have enough margin after the load where you can basically handle this transient due to transition, then you can live with it. You do not have to do anything in that case. Or you have limited your duty cycle very close to 100%, 98% or so, even then maybe you will not get that transient. Otherwise, what is the brute force way? I mean, I do not want to do anything, and I want to limit this. You just increase the output cap. That will limit your undershoot, overshoot. So, that is what people do. If you don't have, if you are not doing any intelligent control, then that is the cost you have to pay. You have to arbitrarily increase the capacitor 3 times, 4 times, whatever, to reduce those transients.